Today we're going to move to this new topics. It's called psychophysics. And the way how you see it is like this. What you should learn so far is that what is a histogram? Is a record of some event accumulated. And then we use that to turn into a transfer function. And that transfer function basically is from 0 to 1, or from everybody survive until everybody's out of the picture, right? That's human life. We pay tax and we die. So that's okay. But on the other hand, when you move from 0 to 1 as your CDF, your transfer function of your reliability is dropped from 1 to 0. And we said that you can do this by using a kind of like, okay, when did the first event happen? When did the second event happen? And then you build up your step function, and then you figure out how to use that to parameterize it. And of course, we're going to do this one more time using SAS, getting into more detail. So the amount of information you should know till now is that I give you a bunch of life and death count. When did it happen? You just turn them into a step function without any problem. Okay. Here's the second part. Okay, when we do that, we said that we come up with a measurement called conditional value at risk. And that at risk means that, okay, by this time, how much left? So we call that VAR. And then CVAR equal to VAR plus the I3 integral from the ceiling to the CDF divided by beta value. And we probably learn how to build that transfer function now. And of course, once you use SAS, will be very smooth. But the next question is that how bad is bad enough? How wrong is wrong enough? How hot the engine is too hot? That a lot of time is human judgment. So VAR is the quantile value. Let me put it this way. In your statistics, a lot of time we set alpha value at 5%, right? So p-value less than 0.05 is significant. But who said alpha value should set at 0.05? Huh? Yeah, it's kind of 20 questions. Okay, if I call it a KGB approach, did you do it? Did you do it? Just keep, slapping the prisoner. Sooner or later, the prisoner will say, yes, 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 I did it. So every 20 questions, as long as there's no, only one. And one out of 20 will consider probably that's the case, okay? But can I have 1%, 1 out of 100? Can I have 0.1%? Sure, you can set it up at any level. For example, I think this is a quote from Colin Powell, the previous Secretary of State. When he was 4-star general before, and he basically, I think it's in his autobiography, talking about when to take actions of something. Let me ask you this. You see a nice job, a nice looking guy or girl, or nice something. Would you wait till you have 100% sure to take actions? Nobody do that, right? But would you do it only 1% of chance? Will you apply a job or something with 1% of chance? Probably not. 2%, 50%. I think Colin Powell said 75%. If you have 75% of you think you're going to make it, you'll do it. So the things becomes, where is that value coming from? We know that you will take risk, okay? For example, right now, would you guys, how many of you, do you play basketball? You don't? No? Okay, let's just find an example. Say you found a job you really, really like, okay? And of course, in order to apply the job, you need to take another course or stay here for 3 more courses, okay? So you're going to delay 1 semester before you graduate. How many of you would do it? Would you say it depends how likely you can get that really, really nice jobs? How high is the pay, and does it worth the effort and the money and the time? Also, probably the look from your classmates or your family and saying that, you must have done something wrong in school. How come you're one semester late, right? So every time when you make decisions, you need to figure out, well, what's the pros and cons and how likely I'm going to make it, right? Remember the first example I give you guys, 6 people got trapped in a cave, gonna join the game to decide who will be the fool. That question coming back again, are you going to take the risk? And the other thing is that doesn't really make sense to have that kind of risk. And that is where the second sections of this semester, we're going to have more into SAS, combine everything and do the integral coming in. But right now, the question becomes psychophysics. The psychophysics basically said that psychophysically, can we turn... The one way to explain what is psychophysics is perception, okay? How to judge the situation and decide what it is and what should I do. And I like to talk about perceptions a lot of time using something very, very out of this world. How many of you like Impressionism painting? Yeah? Who is your number 1 painter in mind? Monet. Okay, let's just do Monet. Okay? And the reason I'm doing Monet is this. Okay? If I'm open up, let's just use the Japanese garden picture here. Okay? And people talk about this all the time, is that, okay? Monet to me is statistics. Why? When he paint, he doesn't paint the detail. He only paint a bunch of dot, light and dark dot. And what does it mean? Is that he will provide you enough dot for you to decide, okay, there is a bridge. No more, no less. So in other words, he's sampling the world through a bunch of dots. Okay? And to sample enough for what? For the receiving end to say that, oh, I see a pretty, young lady, I see something. So the judgment is really, to me, Monet is, even when I talk to a psychologist, I said perception is statistics. Okay? We just judge the world based on the points I have. And of course, a good painter knows how to sample enough, okay? And of course, you can argue this from a different view. Impressionism started when camera available. And once camera available, to make something really, really photorealistic, real, is not impressive anymore. You don't need a painter to do that. Anybody can just take a picture and get it done, right? Just like today, why CNN and all the news networks or newspaper, they're kind of belly up. Because today, everybody got a cell phone. Everybody becomes a reporter, right? Before COVID, a few years ago, in Middle East, there was what they call a revolution. Gaddafi or the dictator got thrown out. Why? Young people, they spread the information through their cell phone. So they can tell each other where the secret police or the riot police gonna gather, and they will move to another point. So in the old days, we get information from CBS, Walter Cronkite, and then CNN. Today, we don't get that kind of news anymore. We can get instant news from everywhere, anytime. I remember, the shootings at UNCC campus that day. I was on campus, and Kennedy is just one building behind, just right behind us. And I heard a helicopter, I heard everything, and I don't have enough information to decide what to do. And guess what? A bunch of international students was outside my office, and they basically tell me the information. Oh, there was a shooting, and then based on the siren, the police, I realized this is going to be a big event, something bad, really, really bad. So what's the next reactions? I better get out of the. I told the student, I said, if we don't get out now, we're going to get locked down. And so I have to decide, okay, should I go or should I stay? And when should I do it? And do you think that's a psychophysical judgment? Because I don't have enough information. I just say, oh, should I go? Should I stay? How long should I wait? If I wait too long, might as well just stay, right? And so psychophysics really is about how you look at the world. And then you're using whatever you collect to decide you're going to do something or not do something. One more example before I get into the math, okay, is this. When you're a kid, have you ever played these games? Standing behind someone and then using one finger, tap your buddy's head and let your buddy and guess, which finger, or did you do it or not doing it. So a lot of time, what is the judgment coming from? Each finger got different amount of force, and you can tell the difference and say that, okay, is there a tapping? How strong is the tapping? Okay? So once I start explaining it this way, psychophysics is everywhere. Whenever you need to make judgment, you need to do that, right? This class ended sometimes 5:15, and then when I got to the parking lot and get out, it was 5:30. And the traffic is horrible, no matter which way I try to get home. And what will happen is a lot of time I have to decide, should I change lane or shouldn't I change lane? And you change lane based on what? Statistics. The two lanes in front of you, which one are more likely to have the clearance to let you beat the traffic light so you won't get stuck behind one more traffic light, right? So the gamble become, I take the switch in order to get enough space so I can be ahead. And what is the gamble usually end up? No matter which lane you do, you're gonna get stuck behind the traffic light anyway, right? So do I give you a mental picture? What is psychophysics now? Okay, so let's do psychophysics 1, okay? Psychophysics 1, and later on, you guys should know a term, okay? The term is called JND, just noticeable difference, okay? And if you out for job interview and you said, oh, how do you decide when to make cut or no cut, lunch or no lunch decisions, and where is that theoretical foundation coming from? Okay, how to survey or calibrate this as psychophysics, and just noticeable difference. One more example, NASA projects. You guys know I did NASA project with Dr. Lim for a while. NASA, every mission, no matter shuttle or Apollo or whatever, they have a countdown, right? 5, 4, 3, 2, 1, launch. Anybody can explain to me why we need countdown? You must have seen it, right? When they launch anything, it will be 5, 4, 3, 2, 1, launch. Right? Yeah? Everything's double checked. So, mission control, fuel, navigations, human factor, crew, safety, even crew, they are psychologically and physiologically. Basically, everybody need to say, good to go, good to go, good to go. Yeah?
Just a very quick fun fact, my dad's coworker's son did the countdown for the last Blue Orders launch.
Really? Cool. Yeah. Were you there?
I was not there.
Yeah.
I was in Florida, of course, but
Yeah. Well, have you ever seen those things?
Yeah.
Yeah. And well, if you can share some video, I will put it with our lecture. So the thing is that countdown is all about psychophysics. The weather guy can say, no, I don't feel comfortable because I see the black cloud coming in and we're getting too close to the thunderstorm. So I don't think we should. So everybody can vote no before the last, the 5, 4, 3, 2, 1 means what? Okay, after this is point of no return, ignition, the engine started, the fuel is ejected into the nozzle, and you cannot stop these things anymore. Okay, so countdowns for that. I can tell you the countdown our dean and the faculty faced just last Friday. What was last Friday? Hurricane, right? And we have advisory board meeting, and guess what? We have football game. We arrange a nice dinner party, and everything's gonna get canceled and wasted. Should we gamble? We keep looking at the news and the weather report. What's the penalty of waste to cancel it? It's really hard to reschedule this. But what is the penalty if we say, okay, we just keep going, everything on time, on schedule? Everybody shows up, and then the hurricane just, get worse and worse straight to us. And who's gonna be responsible for the potential traffic accident, the potential somebody walk on campus hit by a tree branch, right? So psychophysics is really about you decide a threshold, and then we need a threshold to determine later for our entire CVAR computation. Okay, so basically it's about a measurement, and I'm gonna go through this really quickly. In information theory, we talk about, we say this is the information age. So what is information? Just put that down. Information is to do what? If in a job interview, people ask you what's the information, what will be your answer? What is the information? Information is to reduce uncertainty. If I cannot reduce, I'm trying to figure out, should I cancel the Friday's advisory board meeting? Should I launch the rocket? Okay, and you coming in tell me something, there is a war in Europe right now. I will ask, what do I need, why I need to know that? Is that going to reduce my uncertainty for my decisions? If you cannot reduce the uncertainty, you don't want that. And you can also think about this, right? When we build the step function, we already have that in mind. You have a lot of variable. You said that, smoking 2 packs a day and drinks a lot and live in a pretty bad polluted metropolitan area, what do you think the guy's life expectancy, high or low? Low, right? So do you think that he smoked 2 packs a day, living in a bad, polluted city? That's important information about the reliability or survivability, right? So there are 2 sets of judgment. We have 1 set of judgment based on the histogram. That's from the data. And then we're doing this is based on human judgment. Because human judgment sooner or later should coincide with your data. Because in the court, okay, sometimes people will ask, okay, here is a very, very bad industrial accident. Who decided to go ahead, And the weather is really bad, the traffic is really bad, and lawsuit, sooner or later, the jury gonna hear both sides. And one thing they're gonna say is that, do you have enough information to make the judgment? And then if you don't have enough information, why you make the judgment without even ask for more information? Oh, how many of you know one of the shuttles crash is because of the O-rings for the nozzles was cracking? And everybody say, no, we cannot do it, okay? And why they keep doing it? Because the culture basically said that, oh, we need to launch this shuttle. We cannot delay anymore. So people start making judgment by doing what? Hiding the information. Hiding the information, would that reduce the uncertainty? No. Okay, so we need to evaluate. If you take the Bayesian class, I'll explain how to estimate the entropy, okay? Frequency approach versus Bayesian's approach is, one is frequencies approach is the histogram approach. I'm already showing to you, at the beginning of this semester, just how to build histogram. And the other approach is Bayesian's approach is that you have assumptions. And then every time I said, this coin is fair, so it's 0.5, 0.5. But I toss the coin for the next 10 times, it's all head, 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 head. Would you start speculating and say, nah, this is not a fair coins? Based on the number of heads, this is bias, maybe both sides head, right? Okay, and in this, okay, we're gonna start saying that, okay, so if you agree with me, statistics is psychology, impressionism is statistics, so we're using what's happened physically in the world, turn them into psychophysics, okay, from perceptions to psychophysics. We need to use your judgment to discriminate, okay? Discriminate heavy, light, age, whatever, okay? Discrimination actually now is a fully loaded term and with political charge in there. But discrimination in reality basically saying, can you separate the two or separate the three, okay? And detection is, hey, is there something or there's nothing? So, I'm basically will say that, hey, do you think I'm tapping your head or I didn't tap your head? Do you see something pass by or there's nothing pass by? How many of you ever been in this kind of situation? Your loved one, your mom, in the middle of the night and said, I hear something in the backyard. I heard something downstairs. Go check. Have you ever done that? Yeah? And a lot of times, do you think really there's something or just force along? Right? But I'll tell you guys this, okay? whenever someone gives you a false alarm, you know what's the best way to do it? Go do it. Just go check and double check, triple check, because that's the best way to calm people down. Okay, recognition. Okay, is this something strong or something weak? Is this something sick? For example, I tried to get some refill of my medicine this morning, and when I went to the clinics, the receptionist, the first thing said, we got COVID situations again. Give every one of us a mask immediately, even though I have 6 shots. But I said, okay, I'll do it. But why people recognize the situations is severe or not severe? I just walk in, I see everybody's wearing a mask. I know this is, pretty bad situations, right? How many of you got stuck behind an accident, traffic accident, and then you know that this traffic jam is going to be bad? Yeah? How do you know the traffic jam is going to be bad? Or for me is that if I see more than 1 fire trucks and I see more than 1 ambulance, if they only call 1 ambulance, I know the impact's probably 1 victim. But you see more than 1 ambulance, we see 1 fire trucks, it's bad, right? So I'm using something to make the judgment, okay? And next things is about scaling, okay? Scaling, I want you to memorize this and visualize this. Usually there are 4 different types of scale, okay? And this is universal. This is something system engineer should know. The first scale is called nominal scale. Nominal scale means that green, red, blue color, heavy, light, something you can label. So I said that racing horse number 22. That 22 got nothing to do with 21, 20. The 22 only means it's a label of that horse. So that horse is number 22. So the first scale is called nominal scale. Means that you can identify what it is. The second scale is called order or sequential or cardinal. And what does that mean? It means that I can rank everything from small to big, big to small. As long as you can bubble sort it, as long as you can bubble sort anything based on any physics, okay, that is sequential order scale. Okay, next scale is called interval scale. Interval scale means distance. So I'm 5 feet away from you. I could be 100, you could be 95, or you could be -5, I could be 0. As long as our distance is 5, doesn't really matter where is the 0, 0. Okay, that means distance. So let me ask you this. There are 2 classes. I'm the number 1, the best student in my class. And you're the number 1 in your class. So we're equal, both number 1, correct or incorrect? Depends on the difficulty of the class, depends on the scoring and everything. So in other words, I could have, let me give you a pure statistical example. Okay, so let me just have a bunch of random number. Okay, so I can have a bunch of random number, Control C, and paste special value. And then if I sort it, okay. Here, this is, I'm number one. I'm the number one in this class. And if you look at the history, the bar chart of these things, huh? What happened? Okay. This is the A class number one, look like this. Okay. Now let me have a B class number one. I am 88. And then after that, I have a bunch of 87.5. Okay. I am number one. Of B class. Okay? Who is better, number one? Because you feel like there's a fair game in A class. The B class, that 0.5, who knows what happened, right? And let me give you another a class, okay? Based on ranking. And this time, I don't need that. Okay? This time, I still have 88, but everybody else is 40. Okay? Or 40 plus a random number. Okay? Ranking-wise, they are number one. But what's the information disappear in this comparison is that there is no gradient informations about the drops, about ranking. Because by doing the ranking, all you know is that they are number one, but you don't know the score. Interval scale, you know the score, okay? Interval scale, number one, is that you can figure out how to improve something because there's a drop, okay? So, for example, here, this class, the number two can figure out that, I just need to work a little harder, another 4 points, I can be number one. 5 points, I can beat him. But in B game or C game, what's the hard part? A lot of time you don't, in B game, people will say, yeah, you're number one, so what? We are pretty good. Anybody can beat you. And in C game, it's the opposite way. You're number one, but you're a really, really tough number one. Nobody can beat you, okay? So by knowing the differences, okay, the differences, the just noticeable differences, by knowing the differences, we can build a gradient. And build a gradient means that, okay, I can move a little bit harder to get better, okay? And why this is important, for example, I mentioned this in the survival analysis at the beginning. Here, if I said, I would like to, after ABAS, I would like to contribute 2 hours per week extra to help you guys fully understand reliability calculus, okay? Should I help the A student? They're already very good. They don't need me. Should I help the F student? A lot of time, the time if I want to invest will be what? Doing this to the student that with my help, they can move from C or barely make it to Excel, something. So by saying this, actually I will ask you this. Sure, every professor want to be the MIT professor, Stanford professor, but would you agree with me? If you're teaching at MIT at Stanford, the student probably don't need you. They can figure out a lot of things by peer pressure. They compete by themselves. The teachers probably serve more purpose to help, at a state college, because the students sometimes they need a little more nudge than the privileged Ivy League school. Okay, so by saying this, I'm still trying to make you understand nominal scale, no big deal. Just label things. In sequential scale, cardinal scale, just bubble sort. So interval scale is the scale actually give you the direction for improvement. Finally, I'll talk about the last one. The last one is called ratio scale. Okay, ratio scale is the one based on absolute zero. And what's ratio scale? Have you ever heard? Have you ever heard absolute zero? Where you have heard absolute zero? Yeah, or physics, Kelvin. Absolute zero is negative 273 negative Celsius. And why that degree, that temperature? We actually measure that ever? That is a fictional zero. It's based on, a lot of statistics. Basically, we said that temperature is based on vibration of a particle. By reaching that negative 273, there is no energy. In other words, there is no movement, no vibration. Everything's dead. Okay? So if you have an absolute zero, then you can talk about percentage. So ratio scale is about percentage. Okay? But you cannot talk about percentage without the reference of absolute zero. And the people that very, very good in scaling or talk about psychophysics, they are Germans. Okay? In the turn of the, I think it's 19 industrial revolutions, there are two people, and they are very, very one is Weber, one is Fichtner. And they basically try to figure out, can we measure something based on our calibrations and judgment, human judgment. So when you judge, can I pass this car? Do I have enough time to coming back to my own lane? Can I run this red light or yellow light? Do I have enough time to make it? Okay. Can I jump over this ditch? Can I, can I fight this guy? Is he too big for me? They're all based on some psychophysical judgment. And when he tried to do this, he compared that with statistics. And usually the stuff we get involved is intensity, quality, and extension, and last one is durations. How long, how intense, and those terms, okay? Here, Gustav Fichtner, okay, 19th century, and before him is Weber's, and last person is J.J. Stevens. This kind of stuff, I'm only want to mention the name. If you want to go into the history, there are tons of Wikipedia you can use. Okay, so now I would like to go into an example, so you can have some simple homework to do. Okay, and okay, here's the things. Okay, the one we're going to talk about first is called Weber's law. And Weber's law started by doing this, okay? A German physiologist in 1834, again, after industrial revolutions. And why after industrial revolution? Because you have a lot of workers need to judge, do I need to add more fuel to the steam engine? Do I slow down the conveyor belt? Stuff like that. So during the time, you know, they try to discover, you know, how reliable is the human judgment. And here is the first things. Weber in 1834 discovered heavier weight are harder to discriminate and associated with a discriminant alignment. Basically, is this equation. Delta phi over phi is a constant. So here, he basically have two person, okay? He find that every time I add a little bit weight to his body, add a little bit weight to his body, and he said, oh, can you judge? Can you feel it? Can you see it? And sooner or later, this things will level out into a constant. And this constant for delta phi over phi for this black dot subject is about 3.5%. About this white dot subject is somewhere around 2.5%. And how did he run this experiment? Okay, and later he turned them into what we call modified Weber's law, adding a neurological noise, A term. And I think here is we're back to our old regression. Okay, first the data are gonna look like this. Okay, say you run an experiment, you say that, okay, Victoria, come over here. Okay, I'll give you a box. Inside the box, okay, I start putting some weight in there, some paper weight. At the beginning, you know, there is a starting point. That's 30 grams of paper weight in the box, okay? And I ask you to hold the box and say, can you feel the weight? And Victoria, you should say, yeah, I can feel the weight, okay? And the next thing is that I'm start adding weight, okay? There are two different ways you can do this. One is I keep the 30 grams box and start another one. Is 30 grams with a little bit more, 31, 32, and let you compare the two, okay? That require no memory. But then I'm gonna ask you, Victoria, do you feel like one box is heavier than the other box? And you would say, no, I don't feel anything. About the same, 33, 33.2, until I hit 33.99. You said, I know for sure this box is heavier than the other box. And once you do that, okay, I could reduce the weight a little bit and coming back, see if you still say, yeah, about here I can feel the differences. Now, once I have your first delta bill, the delta is 33.99 minus 30, okay? So this is based on this guy minus this guy, okay? And then I will use 33.99 as your new box, or your baseline box. And then I'll have another box, adding a little more, adding a little more, adding a little more. Every time I adding a little more, I'll say, can you feel it? Can you tell the difference? Is there a difference? 36, nothing. 37, nothing. 37.8. And you suddenly say, I can tell they are not the same anymore. So the differences become this guy minus this guy. So you do this 10 times, okay? You have 10 footnotes. So how many differences do you have? You register 10 times, start from 30. If you have 10 observation, 10 number, you have 9 differences. And for each differences, can you calculate a percentage? And the percentage should equal to this number, the D3 number, a D4 number, divided by C4. And now you will have a percentage done. And if you do that all the way, you will have all the percentage done. See that? Okay, so now here I can do the cheap way. Okay, all you need to do now is just say that give me the slope between delta and delta phi and phi, 0.1, about 10%. See that? So that is your Weber constant, 10%. Usually you can tell 10% of differences in this experiment, okay? And remember, I say 30 grams, okay? If this is dog food, it's 30 pounds, that's 33.99. We're basically said that small weight, you have a small ratio, big weight, you have a big ratio, but psychophysically, you probably can tell the differences based on 10% or 11%. And of course, you will calculate another term, okay? This term is called the intercept. But I don't want you guys do this using this approach. So in other words, you know the answer now, okay? Excel will give you the answer. You just need this two number. Okay? You just need this two number, and this two number, all you need to do is have this two data points. Okay, so far so good. We already finished what is Weber's law, a percentage. But if this is the case, then you don't need me, right? This class is over. I would like you to do it manually. And why we want to do it manually? Because we want to explain a couple of things. First, you should give me a term is delta phi times phi. And then you'd have delta phi squared. And why you do that is then you can do a modified Weber's law. And what does modified Weber's law look like is Weber starts his Weber's law, and he said that something's wrong. When you look at the data, you see the constant, but before the constant, there is a initial. The initial, usually the ratio is very, very high, much, much higher than the stable region. And why is that? It's basically saying that we cannot detect at a very, very low level, and so you have a hyperbolic turn right here. And what is this thing? He thinks is internal noise. And everybody, if you try it, cover your ear, and really, really tight, you will start hearing some background noise. Okay? If you close your eyes, you still can see some red lights penetrates through your eyelid. Okay? So no matter which sensor we're talking about, there is a noisy level at the very, very beginning. And he said that in order to cover that, we need to model this using a modified Weber's law by adding a very, very subtly small constant value. And he considers this small value represent the amount of sensory noise that exists when the value of the physics phi is very, very small, close to zero. the actual stimulus can effectively determine the delta phi may not be phi, but rather be phi plus the continuous fluctuating noise, because that noise is always there. But when the way you try to handle is much bigger than, look at here. Every time the A term is a tiny term, when delta phi and phi becomes really big, it's not noticeable. I'll give you an example, okay? Say someone is 22 years old, or let's be legal a little bit. Say 26 years old, dating a teenager 13 years old. We'll say that, hey, that's minor, that's illegal. 23 and 13, they are, he or she is twice the age of the other one, right? 13 years apart, that's unethical. But plus 30 now is what? 56 against 36. It doesn't look that big, 46. So when they say reach 90 years old, that tiny differences is not noticeable anymore. So psychophysically, that's exactly what happened. When you're talking about large value, that is not as bad. But at the beginning, you have to take care of it. So we need to model this phi term. And to do that, okay, and what we really need to do is, I'll get into more detail on the computation later. But first, the determinant is equal to phi squared divided minus the n 9 terms times the delta of the phi. Okay, so this thing's equal to summation of the phi squared divided by n times phi. And please pay attention here. When I do the summations, in the old days, I give real exam in class. Usually people bomb here. Do you see the summation term? I use 10 terms or 9 terms. 9 terms because I only have 9 base. The other one is the jump. And the other thing you need to pay attention to is I use the 9 terms of the first 9 term. In other words, is not from here, from 2nd to 10, is from 1 to 9, okay? And once you have the denominator decided, the slope basically equal to, I'll show you guys later, this is basically simple regressions. Remember when we do regressions? Here, let me find a simple regression here. Simple regression. Okay. And in a simple regression, okay, how to estimate the beta term. Okay, in the denominator, I have the x minus x bar squared. Let me cover this later. Let's because I have cleaner lecture notes to let you visualize. The Wikipedia explanation is too much. Okay. So here is basically, look at here, is d delta phi times c, okay, delta phi times phi minus 9 times the delta phi times phi. Okay, so the first 2 term is still, let me do this. Okay. The slope. One more time. First, talk about denominator. Denominator is phi squared minus 9 times summation phi. Okay? And the slope is equal to the top part, the numerator part, is phi times delta phi. Okay? And minus 9 times of the phi times delta phi. What am I doing here is this, okay? Let me have a simple slide. Insert, shape. Okay. Now, if here is phi, we pretty much like the distribution. We're playing the game here, doing the, okay. So technically speaking, okay, if every time I have a phi measure, when I have a small phi measure and my delta phi is here, and then I said, okay, let me increase my phi measure a little. Fill, no fill, okay. So here's my first observation. Phi and delta phi is here. And then let me have another delta phi measure. This time my phi increased a little bit more, and my delta phi also increased a little more. And then let me have another one. My phi increased a little more, my delta phi increased a little more. Sooner or later, you should see these things kind of proportional, right? The more phi I have, I need more delta to fill the differences. So you do it here, you basically said that, okay, I give you 9 chance. So look at the slope, means what? Summationally, I have a bunch of phi times a bunch of delta phi. A bunch of phi, sum of the phi times delta phi. And then I'm doing this minus 9 times of tiny phi times delta phi, tiny phi times delta phi. Okay? Technically speaking, if every time I did it proportionally, okay? Phi increase a little bit, delta phi increase a little bit, phi increase a little bit, delta phi increase a little bit. That ratio between delta phi and phi is what? Is your slope, right? Agree? So here we're basically just try to estimate that slope by using the differences between phi times delta phi, the area, and how to scale it. We scaled it by using this differences. Means, hey, how much variance? So that's using your phi square minus 9 times of your phi square, right? So denominator really is a variance in disguise. So what is slope? Slope means that I'm increasing phi and delta phi proportionally. Okay, if I did it right, that jump, that little differences should be a constant. But this constant should be weighted by the total variation you have. So this is the first term. And the second term is equal to here. And now I would like you guys first figure out how to do it manually. Okay? If you can calculate regression manually, the intercept divided by the slope is your internal noise. So your internal noise 6.57. Okay? And the slope will be your Weber constant C, modified Weber constant C. So the game I would like you guys to do for homework 1 is you can use my number, or you can come up with a set of number. Basically, just here, how to generate a set of Weber number is very simple. Let me copy this. Okay, you can generate a set of number yourself. You start with a constant. Okay, let's just say I start with a constant 40. And then you just let this equal to this number times a, you know what, I don't want you guys do that part. I'll say that I just use my number for now. Okay. You can copy the PDF number directly, right? Yeah. So just use my number, and I would like you to first figure out a phi, figure out a delta phi, and then estimate approximately what's the changes here. So if you use the average of the changes here, average, okay, it's about 12%, okay? So in other words, is that without that internal noise, you will have a Weber constant a little higher. But with the internal noise, your Weber constant dropped to 10.8, okay? And so everybody agree with me? The first 3 columns is easy computation, right? This is a given. This is finite differences. Here is the constant ratio. And just sum. And once you have the first 2 columns, just use the first 9 pair. You can generate your slope and then your intercept, okay? And once you figure out your slope and your intercept, the next things you want to do is calculate this 2 terms. And because you have those 2 terms, you can easily calculate what is the denominator, what's the slope, what's the intercept, and here. And this 2 numbers should equal to the Excel number, okay? Here, before I go, let me ask you this. If I give you a bunch of X and a bunch of Y, can you figure out their regression? Y equal to AX plus B. Can you do it by yourself? Am I doing anything different from that? No. Delta phi is your Y, phi is your X. Agree? Okay? So I would like you to do it using Excel, but I would like you to at least familiar with these 2 terms, because we're going to get into more and more detail what those terms really means in this class. Okay? I know when I taught DOE, I always cover the geometrical meaning of regressions, and I hope you guys learn. You guys all learn how to do regressions manually, right? Yeah. Okay, so we're good. We're good. Okay, and this class is not about doing the statistical part. It's about how to why statistics really is psychophysics. It's about how to calibrate your feeling. How dangerous is dangerous. Okay. Next, we're gonna talk about Fitchner's law, and next Tuesday. Yeah. And yeah, I don't think I have enough time for Fitchner's law. I'll cover Fitchner's law next time. Okay? Okay, let's call it a day. Thank you.